Welcome to the lecture on solving systems of equations. A system of equations is basically any collection of equations. Typically we will be solving 2 by 2 systems or 3 by 3 systems. A 2 by 2 system is 2 equations in 2 variables, and a 3 by 3 system is 3 equations with 3 variables. When we solve a system of equations, what we're looking for is a point or set of points that makes all the equations true at the same time. So we're going to start by solving 2 by 2 systems of linear equations. So we're going to be talking about 2 lines. And when you think about 2 lines and you're trying to find the solution that makes them both true at the same time, there are 3 possibilities that could happen. The most common possibility is if the 2 lines were to intersect, and your solution would be that intersection point. So that would be a point that's on both lines at the same time. Another possibility with 2 lines is that they could be parallel lines. And if that's the case, there's no intersection at all, so our solution would be the empty set. And then the third case, which isn't quite as common, is if you have 2 equations that may look initially very different. However, when you go to graph them, they turn out to be coinciding lines. So they turn out to be the same line right on top of each other. And in that case, every point on the line makes both equations true since they are both the same line. So your solution is going to look like the equation of a line. And we kind of have a fancy way of writing that with these curly braces, parentheses x comma y, colon, and then you write whichever equation of your line that you want. You can pick that. So your 3 possibilities would be intersecting lines, which have a single point as an answer, parallel lines, which have no solution, or coinciding lines, which would be the equation of a line for your answer. And we will see examples of all 3 of these. So there's several different ways to solve systems of equations. The first method that we're going to use is to solve a system graphically. And to do that, you're going to just take each equation of your line and you're going to graph them right on top of each other. And you're looking for that intersection point. So if we start with this first equation, x plus y equals -5, and we want to graph this, very simple way to graph this because it's in that standard form already. We could find the intercepts. So we could make a little xy table and find the 2 zeros. So we're going to let x be 0 and we're also going to let y be 0. Now if we let x be 0, then this x goes away and all we would have left is y equals -5. If we let y be 0, then the y goes away and all we would have left is x equals -5. So both intercepts are at -5. So 0, -5 would be this y-intercept down here, and -5 comma 0 would be this x-intercept, and my line is just going to be connecting these 2. Okay, so now let's graph the other equation, -2x plus y equals 1. You could also do this with intercepts, but just as an alternative, you could also solve this for y. It's very easy to just add 2x over to the other side, and we would get y equals 2x plus 1, and that puts the equation of the line into slope-intercept form. So your slope m is 2, or 2 over 1, and your b is this y-intercept over here, +1. Remember that slope we're going to think of as rise over run, and 1 is the y-intercept. So when we go to graph this line, you want to start with your y-intercept, which was at 1, put a dot, and then you can use your slope from there. So starting at that 1, our slope was a rise of 2, so up 2 over 1. And there's our second dot. And now we're just going to connect the 2 dots together, and we get a line that looks like that. And what we're looking for when we graph a system of equations like this, the solution is going to be the intersection point, which we can see right here is going to have coordinates of -2, -3. So -2, -3 would be your solution. Now the downside to solving a system graphically is that lines can be crooked. You can have solutions that don't come out to be very nice numbers. If these were fractions or decimals, we wouldn't be able to tell what those answers were exactly from a graph. So a graphical solution isn't the most accurate way to find a solution, but it is very visual, so it has that going for it. To give a little more accuracy to our solutions, we're going to learn two other methods. The next method is called the substitution method, and in this method you're going to take your two equations and you're going to pick one of the equations, whichever one looks easier, and solve it for either x or y, again whichever one is easier. So for example, if I look at this system right here, it looks pretty easy to solve the second equation for y, because all I would have to do is add 8 to both sides. So y would equal 4x plus 8. I'm going to put a box around that because we're going to have to come back to that later. And once you've solved one of your equations for either x or y, then step 2 is going to be to take that whole expression for what in this case y was equal to and substitute it in for y into the first equation, the equation you haven't used yet. And I'm going to want to wrap this in parentheses so that I substitute it in correctly. So basically we're going to rewrite this top equation with y substituted in with 4x plus 8. So that the new equation would look like negative 3x minus 5, and instead of y we're going to put parentheses 4x plus 8 equals negative 17. If you've done this correctly, then you should now have an equation that only has one variable in it, only x's or only y's. And so that should be something that you can solve. All we have to do here is distribute our negative 5 across. So we're going to get minus 3x minus 20x minus 40 equals negative 17. I have a couple like terms here, so negative 3 and negative 20 is negative 23x. And if I add 40 to the other side to get my numbers together, negative 23x equals 23. 40 minus 17 is 23. So if I divide both sides by negative 23, I get x equals negative 1. Put a circle around that. Now that is part of our answer. Remember, when you're giving a solution to a system, it has two parts. It has an x and it has a y. So we just found out what x was. We now need to find out what y is. So that's where we're going to go back to our box over here, and we're going to substitute in negative 1 for this x. So this is going to become y equals 4 times negative 1 plus 8. So negative 4 plus 8, and that gives us y equals 4. So our solution, usually when we write a solution to a system, we write it as an ordered pair. Always put x first and then y. So this would be the solution negative 1 comma 4. Okay, let's try that again. In the next example, same thing. You want to take your equations, look them over, and see what would be easiest to solve for. In this first equation, we already have y solved for. It does have a fraction in it, which may bother some people, but since it already is solved for y, I'm going to go ahead and use it. And that means in the second equation, the one we haven't looked at yet, we're going to substitute in for this y 1/7 x plus 3. So all of this wrapped in parentheses is going to get substituted in for that y. So let's rewrite the second equation. X minus 7 parentheses 1/7 x plus 3, and that's supposed to equal negative 21. So now we have a new equation with only one variable x. Now to solve, we're going to want to distribute our negative 7 across, so we'll get x minus 7 times 1/7. Those two 7's cancel out, so this is just going to be a minus 1x or minus x. Negative 7 times positive 3 is negative 21. And if we go to combine like terms, we see that these two x's cancel each other out. And that's kind of a strange thing that happens. So you want to make sure you look to see what's left over. notice that we still have a minus 21 left on the left side and a minus 21 left on the right side. Now whenever you have an equation or system like this where the variables are canceling themselves out so that there's no variables left, this is going to be one of those special cases. Remember that when you're solving a system of 2 by 2, system with 2 equations, 2 variables, 3 things could happen. You can have an intersection point, like the last example. You could have parallel lines, or you could have coinciding lines. So in this example, based on what's left, negative 21 does equal negative 21, so that's a true statement. So out of our 2 special cases, parallel lines or coinciding lines, which case must this be? Well, it has to be the coinciding lines because we want to get a solution here. And what this true statement says is no matter what I plug in for x, we're always going to get a true statement. In other words, these 2 equations are actually the same exact equation, just written in different forms. You could probably visualize that if you were to take this top equation, multiply through by 7 all the way across, and then just to rearrange some terms, you would end up with this second equation. So these are exactly the same line. So your answer here is that this is a coinciding lines case, but what you want to actually write down for your final answer should be the equation of the line, because every point on the line is going to be shared by these 2 equations since they turn out to be the same line. So our answer is going to look like this. We use this kind of fancy notation, a curly brace, parentheses x comma y, colon, and then after that colon, pick either equation of your line to write down. It doesn't matter which one because they're the same. So I'm going to use the second one here. X minus 7y equals negative 21. And then you just close this off with that curly brace. And what this means is that we are giving for our answer the set of all x comma y's such that x minus 7y equals negative 21. That's what this notation really means if you were to say it out loud. So we're basically saying that every combination of x and y that satisfy x minus 7y equals negative 21 is going to be our solution. Okay, let's try one more example with substitution. On the next example, remember you're trying to find one variable that looks easy to solve for, and in this top equation, y is already solved. So I'm going to go ahead and put my box around that equation, and I'm going to substitute in 2x minus 3 right in for this y. So rewriting the second equation, this becomes 2 parentheses 2x minus 3 minus 4x equals to 4. And if we distribute our 2 across, we'll get 4x minus 6 minus 4x equals 4. And when we go to combine like terms, our 4x's cancel out, and we get negative 6 equals 4. So when you have the case where the x's or the y's are canceling out, then you want to look to see what's left over. Either it will be a true statement, like the last problem, or a false statement, like this problem, since negative 6 does not equal to 4. Now, if it's a false statement, that's basically saying no matter what we pick for x, there's no way this equation is ever going to be true. So there's no x's that are going to work. So our solution here is no solution. And if you want to visualize what this is, these would be parallel lines. These 2 equations, if you were to graph them, look like the same exact line, but they have a different y-intercept. So they're parallel and they would never intersect. So a true statement, like in our earlier example, would give you coinciding lines, and your answer is going to be the equation of the line. A false statement, like our last example, is parallel lines, and your answer is going to be no solution. Okay, so we've talked about the graphing method, we've talked about substitution method, now we're going to talk about the method called elimination. Now elimination is a really useful method. We're going to use this not only to solve 2 by 2 systems, but also 3 by 3 systems. And it's really useful because most of the time your equations are probably going to be written in standard form, which is that pretty form, ax plus by equals to c. So most of the time you already have both equations in that form, and then it's going to be easy to do your elimination because your x's will be lined up, your y's will be lined up, and your numbers will be lined up. So this is how elimination works. First of all, you want to make sure that your x's line up, your y's line up, and your numbers line up. Once they do, you're going to look at either your x's or your y's and decide which one you want to eliminate. And what you're looking to do for that, in order to eliminate a variable, you want the coefficient out front of that variable to be the same number in both equations, but opposite signs. So if I wanted to get rid of x's, I already have a -2 in the second equation. I would need to have a +2 in the top equation. Then those numbers would be the same but opposites. If I wanted to eliminate y's, they both already have a +1 in front. If I just make one of them negative, then they would be opposites. So in that respect, it looks like putting in a negative isn't that hard to do. So let's go ahead and eliminate y. Now to eliminate the y, we need to make these signs become opposites. So we're going to take one equation, it doesn't matter which one, and we're going to multiply through by -1. I can't just put a minus in front of the y because that wouldn't keep the equations equivalent. So to keep the equation balanced, we have to multiply the entire equation by -1 so that it's equivalent to the original one I was given. So let's go ahead and multiply this top equation through by -1. That's going to give me -x, -y equals +5. And the second equation I'm going to leave exactly the same, but I'm going to line it up underneath my top equation. Now if you have them lined up, then you should be ready to add down the columns right away. -x plus -2x is -3x. Because we made the signs on the y's opposites, these y's should always cancel out. And on the right side, 5 plus 1 is 6. So based on this elimination, after eliminating y, you can see that you're left with a really easy equation to solve for x. All we have to do is divide through by -3. So x is -2, and I'm going to put a circle around that. There's part of my answer right there. Now, to get the rest of my answer, remember we need to find out what y is. So unlike substitution, there's no easy boxed equation that we can go back to find out y right away. What we have to do is go back to either one of the two original equations and substitute in -2 in for x and solve for y. So usually I try to pick the equation that looks easiest to work with, and in this case that might be this top one just because the coefficients of x and y are 1s, so it's pretty simple. So I'm going to take that equation, I'm just going to recopy it, and now I'm going to substitute in -2 for that x. And if I solve this for y by adding 2 to both sides, we get y equals -3. So our two solutions are going to be -2 for x and -3 for y. So here's our final solution. Okay, so that's called elimination. Let's try it again. On this next example, we are going to line up our x's, our y's, and our numbers, and they already are here, so we're ready to go. Now what we want to do is decide which variable looks easier to get rid of. Should I eliminate x's or should I eliminate y's? And in this problem, they both look equally the same difficulty. Sorry about that, my pen is acting up on me. So if I want to eliminate x's, for example, I have a -4 coefficient here and a 2 coefficient here. If I were to take this 2 and multiply it by 2, then I would make a 4 here and a -4 here, and that's exactly what we want. The same number but opposite signs. So I'm going to have to take 2 times the entire top equation in order to eliminate the x's. So let's do that. If we multiply through by 2, we'll get 4x minus 6y equals 14. Underneath that, I'm just going to recopy the second equation. And now we're ready to add down. Because we made the coefficients in front of the x's opposites, these should always cancel out. Notice in this problem, the y's also cancel out. So what's left on this left-hand side of the equation? Nothing, just a 0. On the right-hand side, be careful. These are both 14s, but they're not opposites, so they don't cancel out. 14 plus 14 is 28. If your variables all cancel out like this, then remember you want to look to see what's left. Either it's a true statement or a false statement. And in this case, 0 does not equal 28, so this is a false statement. So what does that imply? Remember, that means we're talking about parallel lines. There's no x or y that's going to make 0 equal 28 ever. So there's no solution. And that would be our final answer. Okay, let's try one more. Okay, on this next example, when we try to eliminate either x or y, they're already lined up. To get x's eliminated, since I have a 4 and a 3, you kind of want to think of what a common denominator might be, or in this case a common factor. 12 is divisible by both 3 and 4. So I could fairly easily make these 12s, but I'd have to multiply both equations by something. If I wanted to eliminate y, then I'd probably need to get 6's out front, since 2 times 3 gives me 6. And again, I would have to multiply both equations by something. So it's going to be equal amounts of work to eliminate either x or y. So here you just want to take your pick. Let's say that we want to eliminate x. Then I would need to multiply the top equation by 3, so that 3 times 4 will be 12, and the bottom equation by 4, so that 4 times 3 would be 12. And then remember, not only do we want these to be 12s, but we want them to be opposites. And right now they would both be positive. So pick one of these to be negative. I'll just make the bottom one a negative. So let's multiply the top equation by 3. That's going to give me 12x plus 9y equals 3. Multiplying the bottom equation by minus 4 gives me negative 12x minus 8y equals negative 8. And I should be ready to add down. 12x minus 12x, those should cancel out. 9y minus 8y is 1y, or just y. And 3 minus 8 is negative 5. So here's my y. We now know y. So what we need to do next is find x. So to find x, you go back to your original two equations, pick the one that looks easiest to work with, and substitute in negative 5 for y, so you can solve for x. Now both of these look the same equal difficulty level, so I'm just going to take the second one here. Let me recopy it, and we're going to substitute in negative 5 for that y. So this becomes 3x plus 2 times negative 5 equals 2, or 3x minus 10 equals 2. If I add 10, get 3x equals 12, divide by 3, so x equals 4. So my final solution is 4, negative 5, x, y. Welcome to the lecture on solving systems of equations, focusing on 2x2 systems only. First of all, a system of equations is any collection of equations. A solution to a linear system of equations is a point or set of points that makes both equations true at the same time. So we're going to take a look at 2x2 systems of linear equations, which means two lines, and I want you to think about the two possibilities of what could happen if you were to graph two lines on the same graph. The first thing that could happen, and the most common thing that happens, is that the two lines would intersect, like this first example right here. If they intersect, then there's a single intersection point, an x, y, that makes both lines intersect each other, that makes both lines true, and that would be called the solution. Another possibility, if you were to graph two lines, is they could be parallel. If you think about two parallel lines, when do they intersect? They never do. So in that case, we say that the solution is no solution. The third possibility is a little bit more rare, and this would be the case of coinciding lines. You might have two equations that look totally different, but when you go and you graph them, they end up giving you the same exact line. So where do these two lines coincide, or where do these two lines intersect with each other? They intersect at all the points on the line itself. So in this case, we say that the solution is the equation of the line itself. So the whole line, every point on the line, makes the equation true. Now there's many different ways you can solve a system of equations. The first method that we're going to learn is a graphical method. So how you graph or how you solve a system graphically is to just graph both lines on the same grid and see where they intersect. So let's try that with this first example. First thing I'm going to graph is the top line, x plus y equals -5. Now you can graph this any way you like. It's totally up to you. I'm going to use intercepts to do this. So intercepts are your zeros. So I'm going to make a little table, and I'm going to let x be 0, and I'm going to let y be 0. Now if you were to cover up x and let it be 0, then that's just going to leave you with y equaling -5. If I were to cover up y and make y disappear, then that's going to make x be -5. So just by using my two zeros, I was very easily able to find 2 points that I could plot. 0, -5, and -5, 0. And it's through those 2 points that we graph our line. So here's our first graph. Let's do the same exact thing for the second equation, graphing it. And this time I'm going to just review here a little bit on how to graph this using a different method. Instead of using intercepts, if you prefer, you could graph this using using slope and y-intercept. And in order to do that, I would need to solve this for y. So to solve for y, that just requires adding 2x over to the other side. Then this becomes my b, the constant is your b, and your slope m is that coefficient of x. So m here is 2. I'm going to think of that as 2 over 1, and the 2 is my rise, and the run is my 1. So to graph this, my b is 1. That means your y-intercept, or where the line crosses the x-axis, is at 1. And then from there, I'm going to rise up 2 and over 1. So if I graph these, we're going to get something like this. Now you can probably immediately see one of the issues with solving a system graphically, especially when you're doing this like I am on a computer that's not very accurate. Your lines probably aren't very straight, and you can see that it's a little bit tricky to see exactly where those two lines intersect. Now to be a little bit more accurate, I'm going to use my slope, and instead of going up 2 and over 1, I'm going to go down 2 over 1, down 2 over 1. So this should have hit right there at the coordinates -2 for x and -3 for y. So the exact answer, the exact intersection point, is -2, -3. Now sometimes when you graph lines, they don't line up right on nice grid lines. What if the solution to this had been a fraction or a decimal? Then it probably would have been impossible to tell what the solution is graphically, because we just can't tell decimal answers and fractions from a graph. It's too hard. So there's some other options here for how to solve a system, and these next two methods are the two methods that I would prefer that you use because they're a little bit more accurate. However, the graphical method does give you a nice visual idea of what's really happening when you're trying to solve two equations. So the next method that we're going to learn is called substitution. And just like its name implies, we're going to substitute one equation into the other. Now before we can do that, what we want to do first is solve one of the equations for one of the variables. And it doesn't matter which variable you solve for, either x or y. You just want to do it for whatever's going to be easiest. And you want to work with the equation that's also easiest to solve for. So for example, if we look at this first system, when I look at this, I immediately focus in on that second equation, and to me, that is the one that's easier to work with and easier to solve for. Now, you could quickly solve for x by dividing everything by 4. However, that's going to give you some fractions, and usually we like to avoid fractions if we can. But if I take the second equation and solve it for y instead, which isn't too hard to do. I just add 8 to the other side. Then I get 4x plus 8 is equal to y. I like to put a box around that because we always come back to this equation in the end to finish solving for y. Now what we're going to do for substitution is take that top equation, the one we haven't used yet, and wherever we see y, we're going to substitute in its place this whole expression 4x plus 8. And we're going to wrap it in parentheses. So this is what it would look like. Negative 3x minus, and instead of 5y, I'm going to put minus 5 parentheses 4x plus 8, since that's what y equals. And that needs to equal negative 17. So by doing this substitution, we've now created an equation that only has one variable, x. So we should be able to solve for it. So to solve, I'm going to distribute my negative 5 across. So I get negative 3x minus 20x minus 40 equals negative 17. Combine some like terms, negative 3x and negative 20x is negative 23x. And then I'm going to get my numbers together, so I'm going to add 40 to the other side. And 40 minus 17 is 23. And then to finish it off, divide through by the coefficient of x. And 23 divided by negative 23 is negative 1. So that's what x has to equal in order for these two equations to be true at the same time. And that's only half our answer. We want to get a solution that has an x and a y. So how do we find the value of y? That's what the box is for. If you go back to this box, you're going to substitute in now what x was that we just figured out. So I'm going to substitute in a negative 1 for that x, and I'm going to solve this for y. So we get minus 4 plus 8 equals y, so y has to equal 4. And usually when we write our answers, we write them as an ordered pair, x first, and then y. So these two lines intersect at negative 1, 4. Okay, let's try that again. So here's another system, two equations, two variables. So it's called a 2 by 2 system. And I'm going to do this using substitution. So we would want to look at either equation, whichever one is easier, and substitute in, solve for either x or y. And if you look at that top equation, it's already solved for y. It does have a fraction, so if that bothers you, you don't have to use it. You could use something else instead. But I'm just going to go ahead and use what I've got. And that means in my second equation, wherever I see y, instead of using y, I'm going to substitute in this 1/7 x plus 3. So let's write out what that becomes. Second equation becomes x minus 7, and then instead of y, I'm going to put 1/7 x plus 3 equals negative 21. Now the reason why that fraction didn't bother me so much is because when I distribute here, I can see that that fraction's going to go away. Negative 7 times 1/7, those cancel out. So I just get a negative x. And then negative 7 times 3 is negative 21. Now notice what happens here. X minus x, those cancel out. So that goes to 0, and we're left with negative 21 equals negative 21. Is that true or is that false? That's a true statement. So whenever your variable disappears, you have to look at what's left. And if it's true, like this one is, what does that mean? What it means is that these two equations right here are actually identical equations. If I had taken this second equation and I had solved it for y, I would have gotten exactly this top equation up here. So this is the case of coinciding lines. If I were to graph these two equations on top of each other, they would give me the same exact graph. So what are all the points that lie on both of these equations? Since it's the same line, every point on the equation is going to make it true. So here's how we write our answer, and we kind of use a fancy notation for this. We use curly braces, and then we write the ordered pair x, y, then we put a colon, and then you can write down either equation. It doesn't matter which one you use, because remember, they're the same. So I'll just use the top one. And this is how we would say it. The solution would be the set of all ordered pairs x comma y such that y equals 1/7 x plus 3. So every value of x and y that make this equation true is a solution to this system. Okay? Let's try another one. All right, the last one here on substitution. If you look at your two equations, take the help where you can get it. This top equation here is already solved for y, so we don't have to do any work. We're ready to just go ahead and substitute that expression in for y in the second equation. So the second equation, instead of being 2y, becomes 2 parentheses 2x minus 3, and then I have that minus 4x equals to 4. Now when I try to solve for x, I distribute my 2, and I get 4x minus 6. And notice what's going to happen here again. 4x and a minus 4x cancel out, just like in the last problem. However, what's different is look at what's left. We have a negative 6 equals to a 4, which is obviously false. So what does that mean graphically? That means if I were to graph these two equations, they are what we call parallel lines. So where do they intersect? Nowhere. So if you have a system of equations where the variable cancels out completely, like in these last two examples, if what you're left with is true, then you have coinciding lines, and your answer should be the equation of the line. If what you're left with is false, then you have parallel lines, and your answer should be no solution. So those are kind of your special cases. Alright, so we've talked about solving a system graphically, which isn't always very accurate. Then we've talked about substitution, which works really well. The third method that we're going to use is called elimination. So here's how elimination works. The first thing you want to do is try to get your two equations in what we call standard form, and that's this form ax plus by equals to c. We want to get the x's and the y's on the left side of the equation and the constants on the right side. And if you look at these two equations, these are perfect. They have the x's all lined up and the y's all lined up and the numbers lined up. That's what you want. You want your x's, y's, and numbers all lined up vertically. Now the idea behind elimination is to either pick x and make the two coefficients in front of these two x's be the same number but opposites, or you could also have chosen the y's and make the two coefficients of the y's be the same number but opposites, trying to cancel them out. Doesn't matter which variable you work with. So for example, if I wanted to work with those x's, this coefficient down here is a negative 2. I would really like this one up here to be a 2 as well. Can't just put it in there, however, but there is a way to make it a 2, and that's to multiply the entire equation by 2. You have to multiply the whole equation by 2 to keep it similar, to keep it equivalent to what we had beginning with. So let's distribute the 2 across. This becomes 2x plus 2y equals negative 10. And I'm not going to do anything to the bottom equation. I'm just going to recopy it underneath. So what we've done first here is made these coefficients of x be opposites. Now that they're opposites, we're going to add the two equations together. Because these are opposites, they will cancel each other out, and that x term will disappear. What we're left with is 2y plus y, which is 3y, and negative 10 plus 1, which is negative 9. And that you can solve for y. So all I have to do to solve for y is divide by 3, and now we know what y needs to be. Y needs to be negative 3. Now, how do you find the other half of our answer? Remember, sorry about that, my pen is acting funny today. Remember what we want to do. We want to find an x and a y. So I have y. How do I find x? You need to go back to either of these two original equations, it doesn't matter which one, and you're going to substitute in what y is equal to and solve for x. So let's just take this top one, the one we started with originally, and I'm going to substitute in a negative 3 for y, and to solve for x, I would want to add 3 to both sides, and that tells me that x is negative 2. So my solution is -2, -3. Remember, you can always check that you found the right answer, because if you were to plug in -2, -3 into the first equation, it should give you a true equation. And if you were to plug it into the second equation, it should also be true. This ordered pair that we find needs to make both equations true at the same time. Alright, let's try another one by elimination. So here's another 2 by 2 system, 2 equations, 2 variables. What I want to do is make the coefficients in front of the x's or the y's be the same number but opposites. So this time let's work with the y's. I have a 6 down here and a -3 up here. I want those to be the same number. And an easy way to make that happen is to make this top guy turn into a -6 by multiplying the entire equation by 2. So let's try that. If I distribute 2, I'm going to get 4x minus 6y equals 14. The second equation I'm not going to do anything to. I'm going to leave it the same. And now I'm going to add down my 2 equations. Now we chose the y's to be opposites, so they should automatically cancel out. This problem happens to be a little bit weird because notice the x's also cancel out. So what's left on that left-hand side? 0. Everything's gone. But on the right-hand side, because these are both pluses, this is a 28. And 0 does not equal to 28, so that means these are parallel lines. Whenever you get a false statement, you're talking about 2 lines that are parallel. So when do parallel lines intersect? Never. So your final answer should be no solution. Alright, let's try one more. So here's another 2 by 2 system. We want to either make the x coefficients be the same but opposites, or the y's. It doesn't matter on this one which one you do. They're exactly the same amount of work. So let's just pick x's and make them both be the same but opposites. You've got a 4x and a 3x. So what you want to think about here is it's kind of like thinking about what a good common denominator would be, or a good least common multiple. Here what I want is 12. 4 times 3 would be 12. So how could I make these both be 12s? Well, since this one already has a 4, I would need to multiply by 3. And since this one has a 3, I would need to multiply by 4. Now that's going to make them 12s, but it's not going to make them opposites. So you need to pick one of these to be a negative, and it doesn't matter which one. I'll just make the bottom one negative. So now let's distribute, and I get 12x plus 9y equals to 3. And on the bottom, I get negative 12x minus 8y equals to negative 8. Draw your line and add down. These x's cancel out like we wanted to, and 9y minus 8y is just y. And 3 minus 8 is negative 5. So now we know what y needs to be. So how do we find x? You go back to either of the 2 original equations. It doesn't matter which one you use. I'll just use the top one. And we're going to substitute in negative 5 for y. So this becomes 4x plus 3 times negative 5 equals 1, or 4x minus 15 equals 1. Add 15, so 4x equals 16. Divide by 4, and x equals 4. So my final solution is 4, negative 5. Now most of the time, most instructors, if they give you a problem like this, they're going to try to make them come out evenly. So if you're getting really strange fractions or decimals for your answers, then that means you probably did something wrong. You probably made an arithmetic mistake somewhere along the line. So you want to recheck your answer. Alright, now that we have our 3 methods, graphing, substitution, and elimination, let's try a few word problems. So take a look at this typical mixture problem. You've probably solved these before in your past. This one says that a pharmacist needs 500 milliliters of a 20% phenobarbital solution, but has only 5% and 25% solutions available. Find how many milliliters of each you should mix to get the desired solution. So let's draw a diagram or a picture of what's going on. This pharmacist wants 500 milliliters of a 20% solution by mixing a 5% with a 25% solution. And he's trying to get a 20% solution. So the 5% solution is going to dilute the 25% solution down to a 20. So in these boxes are kind of my rates, my concentrations. How much of each amount do I need? How many milliliters of each do I need? And what amount do I know? We know that we want or need 500 milliliters of the 20% solution. So I'm going to write that underneath here. I know I need to end up with 500 milliliters. We're trying to figure out how many of the other two, or how much of the other two types I'm supposed to use to get that. So since there's two different concentrations, and I want to know each of these two amounts, we can create a system of equations out of this. I'm going to call this amount X and this amount Y. And what do we know about these two amounts? We know that whatever I start with here, this amount here, plus this amount here, when I pour them together, that needs to give me a total of 500 milliliters. So one of my equations has to be X plus Y equals 500. So that's one equation. I need two equations because this is a two-variable problem. So here's how I get my second equation, and that's by using my percentages or my concentrations. We know that rate times amount plus rate times amount has to equal rate times amount. And when you use these rates, you want to use them as decimals. So 5% would be 0.05. So we're going to do 0.05 times the amount X plus 0.25 times the amount Y. And that concentration needs to equal this rate, 0.2 times 500. So rate times amount plus rate times amount equals rate times amount. So here's my second equation right here. So the first equation just deals with the actual amount of milliliters. The second equation uses the rates and deals with the concentrations. Now let's go ahead and figure out what 0.2 times 500 is. It's 100. So I'm going to make this a 100. And now I have my system of equations. And because the x's are lined up, the y's are lined up, and the numbers are lined up, this is all set up and ready to go for probably the elimination method. You could also do substitution if you prefer, but it doesn't matter. I'm going to use elimination. So in order to do that, I want to make these coefficients of x's be opposites. So I'm going to multiply this entire equation by negative 0.05. So that's going to give me negative 0.05x minus 0.05y equals, and now I need to figure out what 0.05 times 500 is. $25, and it's negative because we're using a negative. So there's my top equation multiplied through by negative 0.05. The bottom equation I'm not going to change, so 0.05x plus 0.25y equals 100. And now we're going to add down. The x's should cancel out. Negative 0.05 plus 0.25 is 0.2. 25 minus 5 is 20. So this is 0.2 or 0.20y. And 100 minus 25 is 75. So then to solve for y, divide by 2. And we get 75 divided by 0.2 is 375. So I need 375 milliliters of the 25% solution because that was the y value. Oops, sorry about that. Alright, so we need 375 milliliters of the 25% Okay, so we need 375 milliliters of the 25% solution. Now we want to find out what x is. So when we look back at our two original equations, to me the top one is much simpler and easier to work with than the second one. So that's the one I would choose to use. So x plus y equals 500, and let's substitute in 375 for y. And if I subtract that to the other side, 500 minus 375 is 125. So that's your x. So that's the 5% solution amount. So I need 125 milliliters of the 5% solution. So there's my answer. Okay, so let's try that again with still a mixture problem, but a slightly different type of mixture problem. So here we have a grocer who needs to mix cashews worth $6 per pound with peanuts worth $2 per pound to obtain 10 pounds of a mixture worth $3 per pound. How many pounds of each kind of nut must be used? So instead of having percents or concentrations, here we have price per pound. So that's also kind of a rate. So what are we doing here? We're mixing together first the cashews worth $6 per pound with the peanuts worth $2 per pound, and we're trying to obtain a mixture that's $3 per pound, and we want 10 pounds of that mixture. So this is what your diagram should look like, very, very similar to the mixture problem we did up above. We want to know how many of each type of nut should be used. Since there's two different types of nuts here, we need two different variables. So I'm going to call this one x and this one y. Now your first equation always comes from that bottom row. The number of pounds of cashews plus the number of pounds of peanuts has to total 10 pounds total. So x plus y has to equal 10. The second equation always uses the rates. So we're going to do rate times amount plus rate times amount equals rate times amount. So 6x plus 2y equals 3 times 10, or 30. So here's my system. X plus y equals to 10, and 6x plus 2y equals to 30. Now to solve it, you can use either substitution or elimination. Let's do a substitution on this one since we've been doing a lot of elimination lately. This top equation is very easy to solve for y. All I would have to do is subtract that x to the other side. So let me go ahead and do that. So y is 10 minus x, and I'm going to substitute that in for this y in the second equation. So it becomes 6x plus 2 parentheses 10 minus x. Now if I distribute, I get 6x plus 20 minus 2x equals 30. 6 minus 2 gives me 4x. And then if I subtract 20, I'm going to get 4x equals to 10. And if I divide by 4, that gives me 10/4 or 5/2, or if you want to use a decimal, 2.5. So this one isn't a nice whole number, but it's not too bad of a fraction either. So 2.5. Now that was x. So that's up here, and that's pounds. That's the number of pounds of cashews that we want to use. Now we still need to find y. So to find y using this substitution method, go back to your box and substitute in what x was. So I'm going to substitute in 2.5, and 10 minus 2.5 is 7.5. So that means I need 7.5 pounds of peanuts. So I need 2.5 pounds of cashews and 7.5 pounds of peanuts. And there's my solution. Okay, the next two problems that we're going to do are very similar to word problems you might have seen in the past dealing with distance, rates, and times. But these two problems are very similar to each other because they have some resistance involved. This first one is a plane flying in the air with wind acting as its resistant. resistance. The next problem we're going to do is a boat flowing on the water where the current acts as the resistance. So let's read the problem, then we'll kind of figure out how to set it all up. What we have is when a plane flies with the wind, it can travel 4,200 miles in 6 hours. When the plane flies in the opposite direction against the wind, it takes 7 hours to fly the same distance. Find the speed of the plane in still air and the speed of the wind. Okay? So we're trying to find the speed of the plane and the speed of the wind. So you could use X and Y for that. I'm going to choose letters that are a little bit more obvious what they represent. Let's let P be the speed of the plane. And let's let W be the speed of the wind. Now, if you remember in the problem, it's referring to miles and hours and rates or speeds. So we're going to want to set up a little chart here. Rate, time, and distance. And the relationship between these three things is that rate times time equals to distance. So we're going to make a little chart here. And we're going to have two rows. The top row here I will let be the plane flying with the wind. Sometimes that's called a tailwind. And the bottom row is going to be against the wind. Sometimes that's called a headwind. So let's fill in the numbers that we know. When the plane goes with the wind, it travels 4,200 miles. That's a distance. So I'm going to put 4,200 right here. And it does that in 6 hours. When it goes in the opposite direction against the wind, it takes 7 hours to fly the same distance. So this distance will still be 4,200. Now think about what the rates would be. If the plane is flying with the wind at its back, that's going to help make the plane go even faster. So you've got the wind here pushing plus the plane speed. So the overall net effect is its rate is going to be however fast the plane is plus the wind at its back. So when you're flying with a tailwind, your rate should be P plus W. If you're going against the wind, you've got the plane wanting to go in this direction, but now the wind is up against you, making you go slower. So in this case, when you have a headwind, you're going to be flying as fast as the plane wants to go, P, minus the wind to slow you down. So your rate would be P minus W. And that's going to be the same. Those two expressions are always going to be the same for every problem like this. So we have two variables. We want to get two equations in order to solve this. So here's how we get our equations. We use our formula up here. We're going to take this rate times this time has to equal this distance. And I'm going to use parentheses around this rate since it's this whole quantity. And I like to put the time in front. So I'm going to do 6 times P plus W equals 4,200. And then I'm going to do the same thing for the bottom row. This whole rate times this times 7 has to equal 4,200. So 7 times P minus W has to equal 4,200. So that's how you get your two equations with your two unknowns. Now if you saw this, normally you might be tempted to distribute the 6 and distribute the 7. But I want to show you a shortcut. And this happens quite often with these distance, rate, time problems. Instead of distributing the 6, let's divide both sides by 6. That's going to make this 6 cancel out, and it's going to give us a P plus W by itself equals 4,200 divided by 6 is 700. Now let's do that on the bottom one as well. Instead of multiplying by 7, let's divide both sides by 7. So the 7's go away on the left side, leaving me P minus W. And 4,200 divided by 7 is 600. The reason this is a nice trick is because now, if you look at this, this is perfect for elimination because the W's are already opposites. So I am ready to add down and those W's will cancel out. Don't forget, however, that you want to add your P's. P plus P is 2P, and 7 plus 6 will give me 1,300. A lot of times students forget the 2. So you get a 2P, Now we want to divide by 2, and that tells me that P is 650. That's the plane speed, so that's miles per hour. That's the plane's speed. So we have part of the answer. We still need the wind speed. So how do we find W? You could go back to the original equations, but here's another little tip. I like to go back to one of these right here, because these are going to be a little bit simpler. Since we know P is 650, let's plug in 650 right here, and that plus W is supposed to equal 700. So if we subtract 650, then that forces W to be 50 miles per hour, and that's the wind speed. And we're done. Okay, this next example is very similar to the last one, but instead of planes going with the wind and against the wind, we have a boat rowing with the current and against the current. So if we read the question carefully, we see that with the current, you can row 24 miles in 3 hours, and against the same current, you can row only 2/3 of this distance in 4 hours. Find your rowing speed in still water and the speed of the current. So let's start by defining our variables. We want to find the rowing speed in still water, so that's how fast we would row if there was no current at all, and let's call that R. So R is our rowing speed, and if we let C be our speed of our current, then we want to realize that we're being told things like speeds, which are rates, we're being told miles, which are distances, and hours, which are times. So this is a distance, rate, time kind of a problem. So we want to start by making a chart. Usually we like to put the rates first, and then these get multiplied by our times, and then that product equals our distance. So I'm going to set up a chart, and I'm going to let it have 2 rows and 3 columns. In this first row, we're going to let this row represent going with the current, and in other problems you might see this described as going downstream, and then the second row is going to be going against the current or upstream. So think about going downstream. If you're going downstream, your rate would be however fast you could row plus the current to help you go faster. So your net rate is going to be the rowing speed R plus your current, and that's always true for these problems. When we're going against the current, it's going to be however fast we row minus the current to slow us down. So our net rate will be R minus C. So now let's fill in the times and distances that we know, and these should be given to us in the problem. It says with the current we can row 24 miles, that's a distance, in 3 hours, that's a time. So our time is 3 and our distance is 24. Now against the same current you can row only 2/3 of this distance in 4 hours. So 4 hours is our time, but we don't get to go the full 24 miles, we only go 2/3 of that. So let's figure out what 2/3 of 24 is. 3 divides into 24 8 times. 8 times 2 is 16. So now we have everything filled out in our chart, so we should be able to set up our equation. And our equations are going to come from each row. The first row, we're going to take this rate in parentheses times the time and set it equal to the distance, and then we're going to do the same thing for our second row. So the top equation would give me that time, which is 3, parentheses are multiplied by the rate, which was that R plus C, and that was supposed to equal 24 miles. And then our bottom row is going to give us 4 times R minus C, and that was equal to 16. Now in these kinds of problems, I always find that a nice little trick to do would be to divide through on both sides by your time, instead of distributing the 3 across or the 4 across. You can certainly still do that, but I'll show you in a minute why it's nice to be able to just divide. If we divide both sides by this 3, then the 3's cancel out and we just have that R plus C by itself, and 24 divided by 3 is a nice 8. If we do the same thing on the bottom equation and divide everything by 4, then the 4's cancel out, giving me R minus C, and 16 divided by 4 is 4. Now the reason why that trick of dividing through by the time right away works so well is because what we're left with here is ideal for elimination. The c's are going to cancel out right away if we add down. So that's what I'm going to do. Let's cancel out our c's, and remember we are adding down, so r plus r will be 2r, and 8 plus 4 will be 12. So if we divide both sides by 2, that tells me that my rate r is 6, and r was my rowing speed, so the rowing speed is going to be 6 miles per hour. Now we still want to find our current speed, so you can go back to any of these equations that you want to. I usually like to go back to this one right here because I think it's the simplest. If we have r plus c is equal to 8, and I know now that r is 6, plug it in, subtract 6 from both sides, and that tells me very quickly that c is 2. So our current speed is 2 miles per hour. And that does it for this problem. Alright, let's try one last example, and this one has a little bit of geometry in it. So on this example, we have a rectangular lot whose perimeter is 320 feet, and it's going to be fenced along 3 sides. An expensive fencing along the lot's length costs $16 per foot, and an inexpensive fencing along the lot's 2 side widths costs only $5 per foot. The total cost of the fencing along the 3 sides comes to $2,140. What are the lot's dimensions? Alright, so let's draw a picture. We have this house here, and perhaps we are fencing in the backyard. Okay? We only need fencing along these 2 sides and this length here because the house acts as the fencing or the barrier on the other side. So here's what we've got. We have, let's call this the length L and the width W, since it's a rectangle. So we've got 2 variables involved, length and width. So if we're going to solve this using the system, we need 2 equations because we have 2 variables. So the first equation comes from perimeter. It says that a rectangular lot has perimeter 320 feet. Okay? So how do you find perimeter of a rectangle? Perimeter of a rectangle is 2 lengths plus 2 widths. So 2L plus 2W equals 320. So if we use that as our first equation, we need a second equation, and the second equation is going to come from the fencing. So we know that we want an expensive fencing along the lot's length, and that's $16 per foot. So that's along this length over here. And then the cheaper fencing on the 2 sides is $5 per foot. And the total cost of all this is $2,140. So how do you come up with the cost? If you were going to calculate the cost of this fencing, you know that it's going to cost you $16 per foot times L feet going this direction. So the cost of the expensive side would be 16 times L. What would be the cost of the shorter side? It would be 5 times W, but I have 2 of them. So I need 2 5 times W's. And what was that total cost supposed to be? $2,140. So let's clean this up a little bit. I've got 2L plus 2W equals 320. That was my first equation from perimeter. And then my second one is 16L plus 10W equals 2140. So here are my 2 equations with my 2 unknowns. Now to solve this, I can do it any way I want. I like to do elimination since it's already nicely lined up. And in order to do that, I need to either make my L's or my W's have the same coefficient but opposite sign. So it doesn't matter which one you do. Let's say we want to get rid of the L's. So if this is a 16 on the bottom, I want to make this top one a negative 16, and I can do that by multiplying through by negative 8. So let's go ahead and do that. That means this top equation becomes negative 16L minus 16W equals, and I need my calculator here, 320 times 8 is 2560, and that's negative. The bottom equation I'm not doing anything to. I'm just going to recopy it. So the L should cancel out when I add down. Negative 16 plus 10 is negative 6W. And I need to figure out what 2560 minus 2140 is. So this is going to be 420, but it's going to be negative because the larger number was negative. And then I'm going to divide through by negative 6, which is good because then my two negatives cancel out. And 420 divided by 6 is 70. So the width is 70, and notice our units up here were feet. So the width is 70 feet. Okay, now all we need is the length, and we're done. So I'm going to go back to either of these two equations. It doesn't matter. I'm just going to go back to that perimeter one. And I know that 2L plus 2W, and now I know W is 70, so let's substitute in 70. That has to equal 320. So 2 times 70 is 140. Let's subtract 140 to the other side. And 320 minus 140 equals 180. So when I divide by 2, the length is 90. So L, the length, is 90 feet. And we wanted the lot's dimensions, and we found them both, so we're good to go. Alright, that concludes our lecture on solving systems of equations 2 by 2 systems only. Good luck!